Fluorescence and glow-in-the-dark effects may look like magic, but they are actually beautiful examples of how matter interacts with energy at the atomic level, revealing some of the most fascinating principles of physics and chemistry. Fluorescence occurs when a material absorbs high-energy light, usually ultraviolet UV, and almost instantly re-emits it as visible light. Inside the atoms or molecules of a fluorescent substance, incoming energy excites electrons, pushing them to higher energy states. These excited electrons are unstable and quickly fall back to their original levels, releasing the extra energy as light. Because some energy is lost as heat, the emitted light has a longer wavelength and lower energy than the absorbed light, which is why UV light can produce visible glowing colors. This process happens extremely fast, in billionths of a second, so fluorescence stops immediately when the UV source is removed. This is why fluorescent posters, highlighter ink minerals, and even certain animals like scorpions glow only under UV light and go dark the moment the light is switched off. Glow-in-the-dark materials, on the other hand, rely on a related but distinct phenomenon called phosphorescence. In phosphorescent substances, electrons also absorb energy and jump to higher states, but instead of returning immediately, they become trapped in so-called metastable states. These states act like energy storage zones, slowly releasing light over time. This delayed emission is why glow-in-the-dark toys, watch dials, and safety signs continue to shine for minutes or even hours after the lights go out. Modern glow-in-the-dark materials often use compounds like strontium aluminate, which are far brighter and longer lasting than older zinc sulfide materials. The color of the glow depends on the energy levels of the electrons and the specific chemical structure of the material, producing green, blue, or even orange light. Fluorescence and phosphorescence are not just visual curiosities, they play critical roles in science, medicine, and technology. Fluorescent markers are used in biology to tag cells, proteins, and DNA, allowing scientists to observe life at the microscopic level. Forensic investigators use fluorescence to detect invisible traces of substances at crime scenes. In medicine, fluorescent dyes help doctors visualize blood flow, tumors, and infections. Even everyday items like banknotes use fluorescent inks as a security feature to prevent counterfeiting. Nature also makes remarkable use of fluorescence. Some corals glow brilliantly under blue light, possibly for protection or communication, and certain deep-sea creatures use bioluminescence, a related but chemically driven process, to survive in darkness. At its core, the science of glowing materials reminds us that light is energy, atoms are dynamic, and the invisible world of electrons directly shapes what we see. What appears to be a simple glow is actually a precise dance of energy absorption, electron movement, and light emission governed by the laws of quantum physics. The next time you see something glowing in the dark or shining under UV light, remember that you are witnessing atoms briefly storing and releasing energy in one of nature's most elegant displays. If you enjoyed this deep dive into the real science behind fluorescence and glow-in-the-dark effects, don't forget to like the article, share it with curious minds, and subscribe for more fascinating science explained in a simple and engaging way.